Hello everybody. In our last classes, in few consecutive lectures, we have finished the theoretical part from this chapter, the polar coordinates. Today, we shall discuss some examples on these polar coordinates, on the problems of polar coordinates, especially few standard examples. Let's start with this example. It says that show that the equation of the circle which passes through the focus of the parabola 2a divided by r is equal to 1 plus cos theta. You see over here e is equal to 1. No e is present, so we can say that e is equal to 1. Okay. So this is a parabola. Twice a by r is equal to 1 plus cos theta. And touches it at the point theta is equal to alpha. So we have to find out the equation of the circle which touches the parabola, this parabola at the point whose vectorial angle is theta is equal to alpha. We have to prove that the equation of this circle can be written in this fashion. This is a bit complicated fashion. R cos cube alpha by 2, that is equal to a cos of theta minus 3 alpha by 2. We can say that we can consider this kind of equation. You see, the equation of the conic is given in this way: twice a by r, that is equal to 1 plus not minus. Okay, 1 plus cos of theta. What is the meaning of plus? It means that the directrix and the initial axis, the direction of directrix and the initial axis of this kind of curve, say this is the parabola, they are situated in the same direction with respect to the focus S of the conic. All right, that directrix, the position of the directrix would be like this. So directrix and this direction of initial axis both are in same direction with respect to this focus. Okay, so we can consider the picture of the parabola in this fashion, where where the initial axis should be directed on the left, because the directrix is situated on the left with respect to this focus. Okay, now as because the initial axis is directed on left, therefore the any angle, the vectorial angle of any point, say this is a point, maybe we call it, suppose this is a point P, the vectorial angle of any such point should be measured from the initial axis. Therefore, this is the direction of measurement of any angle. It should be measured from the positive direction of initial axis, so it should be measured in clockwise sense. So as per the picture, the vectorial angles of different points on this kind of conic, all such vectorial angles should be measured in clockwise sense. Okay, so we know that equation of the circle, equation of the circle passing through this kind of focus. Over here it says that the circle touches the point and it passes through the focus. The circle passes through the focus of the conic and touches the conic again at the point theta is equal to alpha. We know that equation of a circle, the polar equation of circle passing through the pole. This is the equation. R is equal to twice b cos of theta minus alpha, where b is a constant quantity and gamma is also a constant quantity. Theta minus gamma. R is equal to twice b cos of theta minus gamma. B is a constant quantity and gamma is a constant quantity. So we need to determine the values of b and gamma. We need to determine the equation of this kind of circle. So if we consider the model equation of the circle in this way, r is equal to twice b cos of theta minus gamma. In that case, we need to determine the expression of this b, the mathematical expression of this b and the expression of this angle gamma. Okay. Um, so what is this? In fact, what is gamma? Gamma would be an angle, and we need to determine that particular angle. And twice b. B is actually the diameter of the circle. Hmm. Sorry, radius of the circle, not diameter. Twice b, and b is the radius of the circle, and twice b is the diameter of the circle. So this much length is actually equal to the length b, the radius of the circle. Hmm. And this angle is equal to alpha if we consider that as per the question that this circle passes this circle touches the conic at the point with vectorial angle alpha. Hmm. So if this is the point at which the circle touches the parabola, see, this is the point at which the circle touches the parabola, and as per the question, this vectorial angle of this point, let us call it P. If this vectorial angle is equal to alpha, then we can say the vectorial angle of this point C, that is also alpha. Hmm. And what is the radius vector of the point C? This much length from the pole. Pole is taken as the focus over here. In this kind of equation, the pole is taken as the focus. So this much length would be is equal to the radius vector of the point C. And what is this length? This length is equal to the radius of the circle. So this much length is equal to B. Hmm. And so we can say that the radius vector of the point C is equal to B, and the vectorial angle is equal to alpha. Got it in this fashion. Hmm. Therefore, we can say that the center C has this kind of coordinate B comma alpha. Hmm. Now you see, just a minute. Yes, B comma alpha. Okay. Now it says that the equation of the circle passes through the focus of the parabola and touches it at the point. And the you see over here this angle alpha is the curve may be a bit different kind of curve. You see over here I have drawn the circle in this fashion. So apparently it looks that the vectorial angle is equal to alpha, but the curve can the circle can also be drawn in this way. Suppose this may be the circle. This kind of circle can also be drawn. This kind of circle can also be drawn, though the picture is not very good. Hmm. And in that case, you see, this kind of this would be the radius, and over here this would be the angle. So it is not that the this would be the angle, and you see over here if we draw this kind of circle, let me draw the circle in a different fashion. Over here you see, let me draw this kind of curve. It would be a bit easier for me to show. Hmm. Let me shift this one. Yes, yes, this is a good picture. And now you see over here, this is the point P. This is the point P. Hmm. And in that case, this would be the radius vector of the point, and therefore this would be the angle alpha. Hmm. And what would be the center from the picture, from the center of this red circle? You see this kind of point. This kind of point would be the center. So the center over here, this kind of point would be the center. Therefore, this angle would be the vectorial angle of the center C. Hmm. So you see, although from the previous picture, from this picture, it looks that alpha is the vectorial angle of the center C. Hmm. But if you consider a different kind of picture, as I considered earlier, in that case, the vectorial angle of the center C may be different from alpha. That's why we consider the vectorial angle of the center as equal to gamma over here. This gamma would be the vectorial angle that is situated in this equation of the circle. Okay, so that's why we consider in this kind of general case that what would be the value of gamma, whether this gamma is equal to alpha or not, that we need to determine. Hmm. So we can say that the vectorial angle of the center C may be taken as equal to any other kind of angle like gamma. But over here from this equation, it is clear that the distance of the point of this center, this distance should always be equal to B. Therefore, the radius vector of this point C, that should be is equal to small b. So we can say that the vectorial angle of this center is equal to B comma gamma. So in any case, we need to determine these two quantities, B and this angle gamma. Got it? And you see, as per the question, hmm, this circle touches this parabola. Hmm. Therefore, we can say that there is a common tangent line, this kind of tangent line. There is a common tangent line which would be tangent to the parabola, and to the circle both. Okay, so this kind of tangent line would be common to the parabola and the circle. And at what point it is tangent, as per the question, we consider this point as equal to P. Its vectorial angle is equal to alpha. Hmm. And we don't know what is the radius vector of the point P. So we consider the radius vector of the point P is equal to R1. Let's write it in this fashion. R1. All right. Hmm. Let us suppose that the vectorial angle of this point P is the vectorial angle of the point P is equal to alpha, and the radius vector is equal to R1. Okay. So the polar coordinates of the point P would be is equal to R1 comma alpha. Okay. Now we try to draw the you see over here, if this is the tangent, then a straight line perpendicular to this tangent, that straight line must be a normal. This kind of straight line must be the normal line. Hmm. And the normal at the point P must pass through this center C. The normal of the point P must pass through this center C. Got it? So let us try to find out what would be the equation of the normal. What would be the equation of this normal that passes through the point C? Hmm? We know the equation of the conic, twice a by r is equal to 1 plus cos theta. So from that equation, we can directly write the equation of the normal in this way. And this normal must pass through the center C. And what was the coordinate of the point C? B comma gamma was the coordinate of the point C. So we put theta is equal to gamma and r is equal to B over here, and we get this relation number 4. So this is the relation number 4 we so far obtained. Now you see on this this was the point P, and P is a point that lies on this conic as well as on the circle. Therefore, these two equations, the equation of the conic and the equation of the circle, both of these two equations must be satisfied by these coordinates of the point capital P. So we put these two coordinates of the point capital P in equation number 1 and in equation number 2. Okay. So over here, you see, if we put these two expressions in equation number 1 and equation number 2, in that case, we get these two relations. This is one relation and this is another relation. Now, from these two relations, we just eliminate this unknown quantity R1. If we eliminate this unknown quantity R1, we get this type of relation, that twice b cos of alpha minus gamma is equal to twice a by 1 plus cos of gamma. And you see, from this relation, this twice a by cos of gamma, this right hand side expression, twice a by 1 plus cos of alpha, twice a by 1 plus cos of alpha, this expression can now be substituted over here. What is this? we actually have this factor twice a. This is numerator divided by 1 plus cos of gamma. Hmm. So twice a by cos of gamma, this expression can be replaced by this kind of expression twice b cos of alpha minus gamma. Okay, so we substitute this relation number 5 in this relation number 4 over here. Hmm? And what we get this kind of result. And if we continue the computation process, then ultimately we get this type of result: sine of twice alpha minus gamma, that is equal to sine of gamma minus alpha. And from that result we will be able to find that gamma is equal to 3 alpha by 2. Okay, so gamma becomes is equal to 3 alpha by 2. Hmm. Now, if we use this result of gamma, gamma is equal to 3 alpha by 2 in this relation, if we put gamma is equal to 3 alpha by 2 in this equation number 5, then we will be compute the value of small b. Okay, then we will be compute the value of small b, and that can be written in this fashion: a divided by 2 cos cube alpha by 2. So we got the expression of small b, we got the expression of gamma. These two were the unknown quantities. Okay, b and gamma, these two were the unknown quantities. So in the equation of the circle, this was assumed to be the equation of the circle. If we now put the value of b and the value of gamma in this equation number 2, then we will be able to compute the final expression of the required circle in this fashion, and this proves the result. Got it? So in this way we will be able to prove the result and compute the equation of the required circle. So next, consider this example. Hmm. Over here we have a variable chord. We have a variable chord of the conic L by R is equal to 1 minus. Remember, we have minus over here. In the previous question we had plus. So we have a variable chord of the conic L by R is equal to 1 minus E cos theta, subtending a constant angle twice beta at the focus. What is the meaning of this? That this kind of chord is actually making an angle twice beta, making an angle twice beta at the focus S, where S is the pole, of course. Show that the locus of the foot of the perpendicular from the focus S on this chord PQ is this kind of curve. We have to find out the locus of the foot of the perpendicular. Okay, the locus of the foot of the perpendicular drawn from the point capital S, that is the pole or the focus on the chord PQ. Hmm. And how is it possible? You see, we have a chord, this kind of chord. This is the point P and this is the point Q. And by question, this chord, that means the point of intersection, these 2 points, this is the point P and this is the point Q. If we draw the lines from P to S, this line and this line, if we draw the line from P to S and from Q to S, PS and QS, these 2 lines will make an angle twice beta. This much would be is equal to twice beta. By question, this much would be is equal to twice beta. Okay, and that is possible if we consider the vectorial angle of the point P is equal to alpha minus beta and alpha plus beta respectively. P have the vectorial angle alpha minus beta and Q have the vectorial angle alpha plus beta. In that case, you see over here the curve is the equation of the curve is taken as L by R is equal to 1 minus E cos theta. So as because it is minus, therefore we can say that with respect to this focus S, with respect to the focus S, the direction of the initial axis and the position of the directrix would be in opposite direction. As because direction of the initial axis is in the right side, the directrix is situated on the left, and vice versa, of course. Over here, as because negative sign is there, therefore you can consider that this is the direction of the initial axis, and therefore the angles should be measured in from this initial axis. So this should be the anti-clockwise. It should be measured in anti-clockwise direction. Okay, and if this is the angle alpha minus beta, then you see this angle would be is equal to alpha minus beta, and this total angle would be is equal to alpha plus beta. This much angle would be is equal to alpha plus beta. That is actually the vectorial angle of the point Q. Hmm. So this much angle would be is equal to the difference between these two angles should be is equal to twice beta. Hmm. That's why the vectorial angles of P and Q are taken as alpha minus beta and alpha plus beta. Got it? And what we need to do? We need to find out the feet of the perpendicular from the focus S. Say this is the feet of the perpendicular. We need to find out the locus of this point. We need to find out the locus of this kind of point, the feet of the perpendicular. Okay. Then what we do over here, we actually try to solve this problem by the help of Cartesian coordinates. We know when this point P and the point Q has this kind of vectorial angles alpha minus beta and alpha pi plus beta, then we can easily compute the expression of the chord PQ. Chord PQ can be computed by this kind by a standard formula. Chord PQ can be computed in this way. You see over here, L is this one is to be replaced by this kind of expression, sake of average by 2, sake of difference by 2. Over here the total difference of the vectorial angle is equal to twice beta, therefore beta is the difference by 2 of the vectorial angles. So sake of beta into cos of theta minus average. You see, if you consider the average of these two vectorial angles, you will get this value alpha. So that is the formula of getting the equation of the chord PQ. So this would be the equation of the chord. L by R is equal to minus E cos theta. You see this minus E cos theta and this minus E cos theta both would remain same. Only this one will be replaced by this kind of expression sec of beta cos of theta minus alpha. And now we cross multiply this expression. This is recomposed in this way. You see cos of theta minus alpha has been decomposed over here, and finally we have taken cos of theta and sine of theta common and separate in two different terms, and then multiply this by r. Then we'll have r cos theta, and that is actually x, and r sine theta would be is equal to y. So over here we have in place of r cos theta we have x, and in place of r sine theta we have y. Okay, and so this would be the equation of the same chord PQ in terms of Cartesian coordinates. All right, in terms of Cartesian coordinate we have this is the equation of the chord. Now you see, if you look at this picture, say this much angle, we suppose what we need to find, we need to find out the locus of this point. We need to find out the locus of this foot of the perpendicular. And if we suppose that this distance, this much distance from the distance of the point from the focus S, the radius vector, if this distance is equal to taken as small p, okay, then the radius vector of the point must be is equal to small p. And you see, if this angle is considered to be gamma, then its vectorial angle would be is equal to gamma. So p comma gamma would be the polar coordinates of this feet of the perpendicular. This is the feet of the perpendicular. So p comma gamma is these two are the vectorial angles of this feet of the perpendicular. And if we write this, and this point is equal to n, then we need to determine the locus of this point n. Okay, So locus means we need to determine some relation involving this small p and gamma. And then we will be able to find out the locus of this point n. Okay, this point n. So over here, you see the locus of this point n, would be determined if you consider this kind of polar coordinates. And you see, we have the normal form of a straight line. You see, this normal form, if you consider this PQ straight line, this perpendicular distance, the perpendicular distance of this point, of this kind of straight line in normal form, if this is P and if this angle is gamma, then we know that the normal form of this kind of straight line, this would be is equal to P cos gamma. P is equal to cos of gamma into x plus sine of gamma into y. This is the normal form of a straight line. So the equation of the chord PQ in normal form can be written in this way: P is equal to cos of gamma into x plus sine of gamma into y. So this is one expression of the chord PQ, and we already computed the another expression of the chord PQ. Over here we computed the equation of the chord PQ as equation number 2, and again the same chord PQ can be represented in different form as equation number 3. So actually we have two different expressions of same straight line PQ. We have two different equations of same straight line PQ. Got it? And therefore we can say that this equation number 2 and equation number 3 must be identical, as because both of these two equations represent same straight line PQ. Therefore we can say that equation number 2 and 3 must be identical to each other, and so we can compare the similar terms. Similar terms means that we can compare the coefficient of x, coefficient of y from these two equations, and similarly we can compare this constant term L and this constant term P. Okay, so we compare similar terms from this equation number 2 and 3, and we get this type of relation. And if we consider this first ratio and second ratio, then we will be able to compute cos of gamma. Similarly, if we consider this first ratio and this last ratio, then we will be able to compute the expression of sine gamma. So we can say that we got the expression of cos of gamma and sine of gamma. And from these two expressions, we observe that we can also compute the expression of cos of alpha and sine of alpha. So we got these two expressions, sine of alpha and cos of sine of alpha and cos of alpha. Now sometimes you get confused that which parameter should we eliminate, whether we should eliminate gamma or we eliminate this alpha. That is a point of confusion. Sometimes it is a bit confusing part. So remember that we always over here we require the relation in between P and gamma. We need to retain this gamma. Otherwise, if we eliminate this gamma, we would not get any relation involving gamma. So we need to retain the expression involving gamma. We need to eliminate the unknown quantities. Okay, so we are keeping this expression gamma, and over here that's why we are just eliminating the other unknown quantities, that is alpha over here. So if we square both of these two equations, take the square of both sides and then add, what we get, cos sine square alpha plus cos square alpha would be is equal to 1. Got it? So if we just square them and add them, ultimately what we get a relation. You see, we get this kind of relation. And what is this kind of relation? In this relation, you observe that we have this kind of quantity P, and this is a gamma. P and gamma. Okay, so we get a relation involving P and gamma, and we were interested in the locus of the point n. We were interested in the locus of the point n. So in this locus, how to determine the locus of this kind of point? this P over here, this P should be replaced by R. And this gamma should be replaced by theta. So everything will be converted in terms of r and theta. You will get the locus. Therefore, just putting p is equal to r and gamma in place of gamma, if we put theta, we will get the locus of the point n. Okay. In this way, we will be able to find out the locus of the point n. So that the equation of the tangent to the conic L by R is equal to 1 plus e cos theta parallel to the tangent at theta is equal to alpha is given by this type of relation. What is this? Let us try to draw a figure because no figure is drawn over here. Let us try to explain this problem by drawing a figure. Suppose we consider a conic. Well, let's for the simplicity we consider an ellipse. Okay. Suppose the ellipse has this kind of equation L by R is equal to 1 plus e cos theta and equation of the tangent to the conic, this kind of conic parallel to the tangent at theta is equal to alpha. Parallel to the tangent at theta is equal to alpha. Suppose there is a point, this kind of point, this kind of point is there, and this is a tangent, and at this point, suppose this kind of point, the vectoral angle, say this is the point P, the vectoral angle of this point is alpha. And we need to determine the equation of another tangent, another this kind of tangent. We need to determine the equation of another tangent like this. Another tangent like this, which would be parallel to the tangent at theta is equal to alpha. This is the tangent at theta is equal to alpha. This at this point, this is the this line. This line is the tangent at the point P. That means at the point theta is equal to alpha, and we need to show or we need to determine the second tangent line, which would be parallel to the first tangent line. That is the tangent at the point theta is equal to alpha. Therefore, we need to determine the equation of this second straight line of the second tangent line, which would be parallel to this first tangent. And we have to show that the equation of this second tangent can be written by this kind of complicated expression. Got it? And how is it possible? We suppose that equation of this second tangent line, say this is the vectoral angle P, and if this is the tangent, this is the equation of the conic, then we know that equation of the tangent at the point alpha can be written by replacing this 1 by cos of theta minus alpha. In that case, we will be able to draw the equation of the conic at the equation of the tangent at the point P. And over here, this is the this might be the sorry, I accidentally deleted this tangent line. This is the tangent line, and this is the point P with vectoral angle alpha. This is the point P with vectoral angle alpha, and this is the equation of the tangent line. Okay. Now we need to find out the equation of another tangent line, which would be parallel to this tangent line given by equation number 2. You see, in case of Cartesian coordinate, if you recall, in case of Cartesian coordinate, suppose we have this kind of straight line Lx plus suppose my plus n is equal to 0. If this is the equation of the equation of a straight line, then parallel to this kind of straight line, if you want to draw another straight line, then the equation would be Lx plus my plus the constant term will be changed. In place of n, we might get another constant k. That was the technique. Now, in case of polar coordinate, what is the technique in case of polar coordinate? In case of polar coordinate, this constant quantity would always come. The effect of constant quantity would always come from this L, because you see whenever r is multiplied by cos theta or sin theta over here on the right hand side, you will get expressions r cos theta is equal to x, r sin theta would be is equal to y. Hmm. So the contribution of from the terms like xy, that would come by multiplication, by the cross multiplication of r with this right hand side. So the only portion that the constant term will, the contribution of constant term will come from this L. Got it? That's why a parallel line will be obtained by replacing this constant L by another constant L prime. Hmm. So we can now write the equation of the tangent line at this kind of point, at tangent line at this kind of point, which is parallel to the original, the first tangent, which is parallel to this first tangent. Such parallel straight lines would have this kind of equation: L prime divided by R, that is equal to cos of theta minus alpha plus E cos of theta. Hmm. Now we need to determine the value of this unknown quantity L prime. Hmm. We need to determine the value of this unknown quantity L prime. And how to do this one? You see, the right hand side expression has been decomposed, and then cos of theta and sin of theta has been separated. And now if we multiply this cos theta and sin theta by r, then in place of r cos theta we will get x, and in place of r sin theta we will get y. So the total expression of, so total equation number 3 can now be converted into this kind of Cartesian form. So we can say that this is the equation number 4, and that is the Cartesian form of this equation number 3. Okay. And you see, we suppose that this point, and this the point at which the second tangent touches this point, if we call it the point Q, and suppose this point has the vectorial angle beta. We suppose that this point Q has the vectorial angle beta. Then just similar to the first tangent, we can we can compute the equation of the second tangent at the point beta, at the point having vectorial angle beta. And that is also done over here. The at the point Q with vectorial angles beta, we draw the tangent line. You see, the tangent line will be L by R is equal to cos of theta minus beta plus E cos of theta. And again, this is also converted into Cartesian form. So we actually have two different equations. We actually have two different equations. One is the equation number 5, another is the equation number 4. 5 and 4 both are written in Cartesian form. Okay, 5 and 4, this equation number 4 and this equation number 5, both are written in Cartesian form, and both are actually the equation of the tangent at the point Q. Both are actually the equation of the tangent at this point Q. Okay, so we have the equation of a single straight line given by equation number 4 and equation number 5. So 4 and 5 both represent same tangent line. Equation number 4 and equation number 5 both represent same tangent line. So we can say that equation number 4 and 5 are identical to each other, and we can compare the similar terms. If we compare the similar terms, then we get this type of relation. Similar terms means the coefficient of x divided by the coefficient of x, we will get this kind of ratio. Then if we compare the coefficient of y, we will get this kind of ratio. If we compare the constant terms, we will get this kind of ratio. Okay, so in this way we will be able to get this ratio. And if we compare the last ratio and the first ratio, we will be able to compute sine of beta. Again, from first ratio and from this second ratio and first ratio, from this relation, we will be able to compute the expression of cos of beta. And so if we square them and add them, sine square beta plus cos square beta would be is equal to 1. Okay, sine square beta and cos square beta would be is equal to 1. So we can say that this expression is actually is equal to 1. And on the right hand side, we will get this kind of complicated expression. And the total right hand side is kept in terms of L by L prime. We are not decomposing this expression L by L prime. We are keeping this fixed because you see, with respect to L by L prime, you see over here this total expression can be written in this way: L by L prime whole square into some quantity, then some term involving L by L prime, and then some term without L by L prime. So we can say that this is actually the equation in terms of L by L prime, and that would be the second degree equation. Okay, so that is actually a second degree equation. So we can solve this equation. Computation is a bit difficult over here, laborious, not difficult, a bit laborious. Anyway, so over here we can compute L by L prime, and after the simplification we find that we get two different values of L by L prime. One is the value L, and another is this kind of value. One is the value 1, not L. One is the value, this is the one value, and another is this kind of value. Now you see, if L by L prime is equal to 1, if L by L prime is equal to 1, then L and L prime both become same. And if L becomes is equal to L prime, you see, if L becomes is equal to L prime, in that case, we would get this equation number 2. If L becomes is equal to L prime, we will get this equation number 2. Got it? And equation number 2 is actually the tangent line at the point P, but we are not interested in this tangent line. Rather, we are interested in the tangent line at the point Q. Got it? That's why L is not equal to L prime. But because if L becomes is equal to L prime, then we will be able to get this tangent line, not this the second tangent line. We are interested in this second tangent line. Okay, that's why we are not taking this value L by L prime is equal to 1. We are not considering this value. Rather, we are considering this second value. L by L prime is equal to this category, this kind of expression, e square minus 1 divided by 1 plus e square plus twice e cos of alpha. Therefore, L can be written in this way. And now if we put the expression of L in the equation number 3, if we put the expression of L in the equation number 3, then we will be able to compute the equation of this second tangent line. Got it? If we put the expression of L prime in equation number 3, then we will be able to get the equation of the second tangent line at the point Q. And if we put this result, ultimately by simplification, we get this final result. This is the final result, the equation of the second tangent line. Okay, so in this way we compute the equation of the second tangent line. So you please go through this kind of examples. Okay, I'm not going to discuss all these examples because it is not practically possible. You can go through these examples. Even you see, this is also an important example. This example number 15. Sometimes I could not draw all the pictures because drawing the pictures and making this kind of file is a bit difficult task for one person. So you please try to draw this kind of curve, this kind of figures by yourself. I have given the total computation, but sometimes I could not draw all this kind of curves. So this example number 15, then this example number 16. These were very important examples.